In this video, let's discuss the best estimate. The estimation problem is formulated as use observations YT to determine the best estimate of ST1. We know ST1 is a random variable. To know the random variable, we must know the probability distribution. So since here, so the only measured variable is YT, so therefore we need to know the conditional distribution of ST1 conditioned on YT. All relevant statistical information which the observation YT can provide about the random variable ST1 is contained in a conditional distribution. So the efficacy YT is a conditional distribution. Based on the definition we know, so this is defined as the probability of ST1 less than or equal to C conditioned on the YT. If we know the conditional distribution, then we know everything about the random variable ST1 conditioned on the realization YT. Let's also define the conditional density function. Let's use the notation efficacy YT to denote the conditional density function of ST1 conditioned on YT. To completely specify the estimation problem, we need to define the criterion which defines the best estimate. So here, let's assume, so the best estimate is defined as the one which minimizes the mean value of a loss function J. So the problem is to minimize the mean value of J s minus x hat. So J is a real function. So it's very important to distinguish between unconditional mean and conditional mean. So here we want to minimize the unconditional mean. To distinguish the two, let's write the criterion in such a way that dependence of x hat on YT is explicit. So there are two expectations. So the first expectation is with respect to S. We know S is a random variable. So this is the average of the loss function J s minus x hat conditioned on the realization YT. So the YT here is not a random variable anymore. Okay. So given the realization, so all available information want to minimize the average of J s minus x hat. Then the second expectation is respect to YT. We know YT itself, okay, is also a stochastic process. It's several random variables from T0 to T. So therefore, so this is the unconditional mean. We first take the expectation with respect to the conditional mean of S minus x hat. Then we take the expectation with respect to this realization. There could be many possible realizations. Then we take an average of all possible realizations from T0 to T. So let's also define the conditional mean. So conditional mean is defined in this way. So this is the expectation of J s minus x hat conditioned on YT. So if we know the conditional density functions, so this can be calculated in this way. So this is integration from negative infinity to positive infinity. This is a range of C. It's J C minus x hat. So this is a conditional density function f C conditioned on YT d C. To minimize the conditional mean with respect to all functions. So here it's with respect to all functions. So this minimization is respect to all functions. So this function it's a function which maps from y to s. The argument is yt's a realization, any realization. You calculate a value, the value is x hat. Okay, x hat here, we use, it's kind of like a Abusor notation. We use x hat as a function, also it as a value. The function of the value of the function as the estimate of s. To minimize the conditional mean here with respect to all possible functions is equivalent to minimize the conditional mean. We know if this function can minimize all possible realizations, of course, it will minimize one particular realizations yt. If this function can minimize every realization yt, so therefore it will minimize the conditional mean. So when we take the expectation with respect to all realizations, then I would like to introduce the following theorem. So I will not show the proof. The proof can be found on page 213 in the textbook. So the theorem is stated like this. So assume the conditional distribution, so this is f c yt, the conditional distribution of xt1 given yt has a density function, so that's f c yt. The density function is symmetric around the conditional mean. The conditional mean can be calculated in this way. So this is all possible values of c from negative infinity to positive infinity times the conditional density f c conditional yt dc. The density function is symmetric around the mean and non-increasing for c greater or equal to m. So in general, the density function is something like this. So this is a density function. So we have a c here. So this is the f c conditioned on yt. So let's assume here is a mean value. The function is symmetric around the mean value and non-increasing for c is greater than m. The function will be, the density function will be something like this. Then the sum from negative infinity to positive infinity is 1. Then it has the highest value when c is m. This is a mean value. The loss function, let's assume the loss function j. This is a j. We want to minimize the average of the loss function. The loss function be symmetric, also symmetric around 0, symmetric around 0, and non-decreasing for positive argument. So the loss function, it will be defined like this. So the loss function, it will be something like this. Like say this is the x, this is the, maybe let's use a different notation. So the jx. So this function is symmetric around 0 and non-decreasing for positive argument. So it'll be something like this. Then this theorem tells us if the probability density function is symmetric around the conditional mean and non-increasing for c greater or equal to m, and the loss function j is symmetric around 0 and non-decreasing for positive argument, then the best estimate for the unconditional mean and the conditional mean is then given by the conditional mean. So the conditional mean is an estimator, it's the best estimator given yt. So the estimator, the best estimator, x hat is be the x hat is a function of yt, so that's the expectation of s conditioned on YT. So that's the C F C YT D C. So in other words, it will be just the M. That means, so the best, in this case, so the best estimate is just estimate the mean value. So the mean value will be the best estimation of S. I'll give two remarks. So based on the theorem, if we know the conditional density function satisfies the condition of the theorem, so that's the conditional density function is symmetric around the mean and non-increasing for C greater or equal to M, then the choice of the loss function is immaterial if it is symmetric, if the loss function is symmetric and non-decreasing for the positive argument. So in other words, that means, so if the probability density function satisfies the condition of the theorem and the loss function satisfies the condition of the theorem, then the detailed form of the conditional density function and the detailed form of the loss function do not matter. They can be, if they satisfy these conditions in the theorem, so their detailed forms do not matter. Then the next remark tells us the conditional mean will not always give the solution to the estimation problems. If the conditional density function or the loss function does not satisfy the condition of the theorem. So for example, if the density function is not symmetric around the mean, then the best estimate of the unconditional mean may not be the conditional mean. Or if the loss function is not symmetric around 0 and not non-decreasing for positive arguments, then the best estimate of the unconditional mean of J may not be the conditional mean.